Hi everyone, Mr. Stansberry here. We are going to review De Morgan's Law. All right, so first off, who is De Morgan? Well, Auguste De Morgan, he was a British mathematician and logistician. And what he said was, he said that this, not A and B, is logically equivalent to not A or not B. Well, this is just one of the things that he said, and we'll look at some of the other combinations. But I would just like to say, what? Like, how is and or, like, how does and switch to or and all that kind of stuff? Well, I think it's important to go back to algebra class, right? So remember in algebra when you had to graph this compound inequality, right? We have a is greater than 3 and a is less than or equal to 7. Well, to graph this, first thing we would do is give ourselves a place on the number line where we're going to plot the 3 and the 7. And we would need an open circle for this greater than sign, right? That's that rule. And we would need a closed circle for the less than or equal to, right? Because we can actually equal that value 7, and in this case we're not allowed to have 3 as the value, right? And then to graph the and, we simply shade in between these two numbers, right? That makes sense. So a must be greater than 3 and a must be less than or equal to 7. That's how we graph it. Okay, but what is not this? Right? What is not this? Well, if you think about it, not this is the inverse, right? It's the inverse of the original graph that we had, and this is the inverse. So the inverse to this is a is less than or equal to 3, because if you notice that circle changed from open to closed, and then the other side of not a is less than or equal to 7 becomes a is greater than 7. All right, that's interesting. And then remember when you had to graph these in algebra class, what this was, where we had the arrows or the shading going in the opposite direction? That was or, right? That was or. So hopefully this kind of draws a connection to what's going on in this De Morgan's law. A lot of people use the set or the Venn diagrams or the set stuff to show this, but I kind of want to meet you where, it's something that you've seen before, hopefully in algebra class. So just kind of a different way to attack this. Now, let's go back to that original statement, not A and B. Well, we know that not A is equal to, well, not A, right? And then and is going to switch to the or, just like we saw in that number line. And then not B is not B. Okay, that's great. That works. Another way we can, I should also show you that these are the different statements that are part of De Morgan's, right? So not A and B is equal to not A or not B. Not A or B is equal to not A and not B, right? The or changes to and in this case. And then because this is an equal sign, it's an identity, right? We can just simply switch them and put them on the opposite side to the equal sign. And you should be looking for this on that AP exam. They may show you these things in different forms, right? And you need to be able to pick it out. Okay, that's all well and good. Another thing that you can do to prove De Morgan's law, in some cases it's pretty easy, is to use a truth table. Right, so in the De Morgan's law that I showed you, we only had 2 inputs, A and B. And if you've got 2 inputs, you have a total of 4 possible outputs. That's why I have only 4 rows in this table. All right, so what can A be? Well, whenever I'm filling out these truth tables, for the first value I have here, I'll make half of them true and half of them false. And then the last one is simply going to alternate between true and false. That's a really nice way of getting all possible combinations. So these are all possible combinations that a truth table could hold for only 2 inputs, A and B. All right, so let's fill out the rest of this. And I should also say that what I'm trying to show you here is that not A and B is logically equivalent to not A or not B. Logically equivalent, meaning for a given input for A and B, these 2 things should be the same in every case to be logically equivalent. Okay, so let's continue. All right, so if I have A is true, true, false, false. Well, not A is the opposite of that, right? Not true is false, not true is false, not false is true, and so on. Not B, same thing. I just take the opposite of B. Now, A and B, I'm going to go back to A and B. Remember, for A and B to be true, both things have to be true. So I'm going to look at that. True and true is false. True and true is true. Everything else is false, okay? So that's what we get for A and B. So not A and B is the opposite of this column, right? It's the opposite. Okay, great. So we have the logical values for not A and B, not A and B. We get false, true, true, true. Now, our De Morgan says that these two things are logically equivalent. Is that true? Well, let's find out. I'm going to cheat a little bit here for just to make room in the my table. I would have done not A, or I would have done A or B, right? Just like I did A and B, but needed some space. All right, so let's just talk this out. Or means that only one of these sides has to be true in order for the outcome to be true. All right, so let's see. So not A is false in this case, for A being true and B being true. Not A is false or false. So false or false gives us false, okay? False or true gives us true. True or false gives us true, and true or true gives us true. All right, so hopefully you see that for a given input A and B, these two, what De Morgan says are logically equivalent, are the same for all cases that A and B could be. So we can say that these two statements are logically equivalent, just as De Morgan says. Okay, hopefully that helps.